Further to that Facebook post regarding carbon fibre, just out of interest, if anybody wanted to see the type of process that goes into the traditional carbon fibre process and designing carbon fibre bits, I've got a simple demo on a little toy drone here. If we take this top, this is an assembly, consists of a number of parts. You can see each of the individual components in the assembly. If we just take this drone top and work on that one, so you can see you've got all the details, the lips and what we do, the rim around the edge, the lips around the edge, whatever you want to call it. I've done a load of pre-prep on this to get it into a position where it's ready to go. Extracted a load of geometry and even created some additional curves in here, which you'll see what these are for in a bit. So this zero thickness surface is used to help define the carbon fibre plies and the laminate. It's extended a couple of mil because it'll always be trimmed back when it comes out of the mould, or if it's going to be joined together it'll need an overlap so the two halves can be bonded together as well, or joined together. So starting off with then, we need to create a layup surface, and that layup surface is actually already pre-done in here. And we also need a composite region, and the composite region will be a boundary of the sheet edges. So I've already done those, the composite layup surface. It's got a direction. If we go to this composites navigator, we need a rosette. A rosette is what we would normally use to define the orientation of the plies. And when you've got carbon fibre, which is basically a woven sheet with each of the weave directions being at 90 degrees to each other, when they put the plies one on top of the other, they tend to orient them at 45 degrees. For strength, so you've never got two sheets running in the same direction, ideally. So this is used to help define the ply orientation. Once we're in there, we can create the layup, the laminate, and we can pick the rosette, and you can see it starts to build our composite part and laminate one. Once we've done that, we can go into the ply here, and we pick a composite region, which is going to be the boundary. What the orientation is, so 0, 45, minus 45, 90, 180 or whatever. I've got a fictitious material, just a 2x2 mil weave. I'll choose OK. There's the ply. Once you've done your first ply, you can actually run a producibility, so people will use tools like this to select the ply, specify the origin. This will be where they aim to lay the carbon fibre down, the sheet that the laminate down. We can set this cell size to go to 3 mil and run producibility, and you can see it gives you what the flat pattern would look like. And if I just make this window a bit bigger, you can see I've got a nice contiguous edge or continuous curve around the edge, but we've got these red areas, and if you think about that analogy in the Facebook post, if you saw it, of trying to get an A4 piece of paper and wrap it around a breakfast cereal bowl, you're obviously going to get wrinkling, and these areas are where the carbon fibre and these simulate the weave directions would wrinkle in the corners. So what we can do is use these curves here to create darts. You'll see at the top I've got this dart command, and I can pick the ply and then select the geometry, and you'll see it extends these to the edge, and we basically pick all these around the part. I'm actually picking all the curves in one go rather than run a couple of producibility checks, but you'll see this is out of date. If I just update the results on this and then show the result, you can see how it's affected the colours in the simulation. We've got very little red. We could probably get away with that now in a mould. And if I just right click on this and publish a flat pattern, so this is what you would export that goes to your cutters that cut out all the different laminates. If we go and look at what one of these looks like in the window, you're going to see that the flat pattern that you would need to create that part is no longer just a nice continuous, well, it is a continuous set of curves, but it's not nice. It doesn't sort of represent what you'd think from a flat pattern. You've got all these little cuts that you would need to put into each of the plies to allow you to form this around complex shapes. So that's all well and easy on something like this, which is very simple in shape, or even on your bigger parts of a mountain bike frame or any bike frame that have got very gradual changes in topology. But where you get into areas where you've got really complex topology or really tight corners, you can imagine that trying to cut out really complicated flat pattern shapes gets quite challenging, and no wonder you get inconsistencies in wall thickness when you're building shapes like this that have got really complex structures, especially mass producing them as well. And if things have been done for Olympic bikes and things like that, then there's obviously a lot more care and laser alignment and all those things going into the production. But when they're banging these out by the thousand in the Far East or wherever they're made, then quality control and the consistency that you won't get with an Atherton tube is massively prevalent. And I've seen it in places where I've squeezed top tubes on bikes before, and you'll squeeze it down here and it's rock solid, you can barely squeeze it. You move along here a few inches or get closer down here and you can actually squeeze it as though it's made out of some thin plastic. Anyway, thanks very much, hope you enjoyed it. Cheers.